Alright, so today we're going to be talking about some properties of definite integrals and then cover something called antiderivatives. So let's just get into it. So we kind of introduced definite integrals, and to be really able to use definite integrals and just evaluate them in various cases, it's important to know some properties of them. So we're going to go over 7 different properties. So let's just start. The first one is called the order of integration. And this property states that the integral from a to b of f of x dx is equal to the negative integral from a to, or the negative integral from b to a of f of x dx. And then for these properties, like some of them, the proof is beyond the scope, but hopefully I can give some intuition of why this makes sense. And so for the first one, um, the reason why this is true is because when we're finding these areas, like let's go back to Riemann sums, right? We're gonna have some boxes like this, right? That approximate the area of the curve, right? And our dx, when we're going from a to b, right? So this is a and this is b, we're going right? And then over here, these delta x's are gonna be positive, right? But when we're going from b to a, now we've shifted the direction, right? The curve still remains the same, but now we're going from b to a. And so while the size of the delta x is the same, because we're going from b to a, the the delta x is now negative because we're going from bigger to smaller. So these, like if I had delta x2 over here, this delta x2, like let's just call it prime, delta x2 prime is simply negative of delta x2. So the only thing that has changed from this first scenario to the second scenario is that our widths are now negative. And because the fact that the widths are now negative, our overall integral, whatever it evaluates to, our definite integral, whatever value it evaluates to, it's going to be the negative of the value it evaluates to when we went from A to B. So in general, the idea is like whenever you switch the limits of whenever you switch the upper and lower limits, the value the integral evaluates to becomes negative. So that's the order of integration rule. The second is the zero property. And this one states that the integral from a to a, so our upper and lower limits are the same for any function f of x dx is simply equal to 0. And intuitively, this kind of makes sense, right? We're saying that the size of our interval that we're measuring our area over is simply 0. So our width is 0, right? So whenever you have a 0 width, no matter what your height is going to be, the area is going to be 0. And so that's why you have the 0 property. The third property is called the constant multiple. And this one states that the integral from a to b of k times f of x dx is simply equal to k times the integral from a to b of f of x dx. So this kind of states that if you have a constant term outside of your function, you can just find the integral of the normal function itself and then scale it by the constant. And so the constant term only acts like a scaling factor for an overall area. And again, to motivate this, and this is like not a proof at all, it's just like a rough motivation. Let's say we had a curve that looked like, you know, something like this, right? And now we're scaling all of these values by some multiple like k, and let's just make, like, for loss of generality, like k is greater than 1, right? And so we're scaling these values, so we're gonna have something like that looks like this, right? If let's just say here k is 2, so like all my heights have doubled, right? And so before, when I was trying to find the area, each slice had like some height x, right? And now the height becomes 2x. So each slice has double the value. And since the integration is just finding the sum of all these infinitesimally small slices, and the fact that each of these infinitesimally small slices are scaled now by a factor of k, our final value for the like our final thing that our integral evaluates to is also a scaled version. So in the end, if you have a constant that we're multiplying by, our final value that it evaluates to is just a scaled version by that constant. And a lot of times, people forget that negative, like, let's say you have a to b negative f of x dx. Remember that this negative is the same thing as a to b of -1 times f of x dx, right? So then the constant rule still applies to this. So you can take the negative out and just evaluate f of x dx, right? And remember, through the order of integration rule, this is also the same thing as b to a of f of x dx. So there's multiple ways to evaluate it, and depending on whatever the function is and what's easier, you can choose to you just choose to like pick whatever flavor works for you. But yeah, so I just explicitly wrote this example out because a lot of times people forget about the negative. So let's go on to the next rule. This fourth rule is called sum and difference. And so this one states that the integral from a to b of f of x plus or minus g of x dx is the same thing as evaluating each of those integrals separately. So essentially what this is saying is if you have two functions that are like summed together, you can split those functions up and evaluate the integrals of those functions separately, and then simply just sum or find the difference of all of those. And again, like the rough motivation is, let's say you had like a function, this so h of x is equal to f of x plus g of x, and so the original function is to find the area of h of x under some interval a to b. And so if h of x looks something like this, right, and like in reality is a sum of like f of x plus like, you know, some g of x that like introduce this curvature like this, right? Then we can kind of think about this h of x strip as being the sum of like this tinier strip over here, and then the sum of the other. Or let me actually change the color. So this right. So we can kind of think about like if we were told to find the area of like h of x dx, right? So each of these rectangles, so this is for h of x, consists of the sum of like this rectangle, like this subrectangle, and this other subrectangle, right? So when those like little two subrectangles are added up together like this, it forms the entire area of the strip. So like this little subrectangle goes over here, and this other one goes over here, right? And so that is what allows us to split the overall integral into two separate integrals and then just use this sum form, like the sum. Note that you cannot do this with multiplication, but when you have a sum or difference, you can do it. So that was the sum and difference rule, and hopefully the rough like motivation that I showed you kind of convinced you. The next property kind of flows from the property, and oh, I should probably name the property. So the next property is called additivity. Additivity. And then this one says that the integral from a to b of f of x dx plus the integral from b to c of f of x dx is simply equal to the integral from a to c of f of x dx, right? And we can also think about this as making logical sense, because let's say this is like the interval a to b, and then you have some interval from b to c, right? And then this, we have some waveform function that looks like this. If we separately calculated out this area, and we call this A1, and then we separately calculated out A2 as being this area, and we want to query for the area from A to C, we can just simply add up A1 and A2 together, right? And so the overall integral from A to C is simply like the sum of the area between B to C, represented by this integral, and then the area of A to B represented by this integral. So you can always split the large interval into some subintervals and find the integrals of those, and then in the end, if you sum them up, you'll get the overall integral. So that's the property of additivity. Our sixth property is called the max-min inequality. This one states that if f max and f sub min are the maximum and minimum values of f on the interval a to b, then f min, so it's like the value of f min times b minus a, is less than or equal to the integral from a to b of f of x dx, and it's less than or equal to f max times b minus a. And again, this kind of makes sense, right? So this max-min identity is just for us to be able to lower bound. So this is like a lower bound on the value of the integral, and then over here we form an upper bound of the value of the integral. And so all we're saying is that on some interval, if we know the maximum value and if we know the minimum value that the function takes on, we can then lower bound and upper bound the value of the definite integral on that interval as well. And that kind of makes sense, right? Let's say if you had like some curve that looks like this, right? Now, if I want to find the integral between a and b, or at least just like estimate what the maximum value and the minimum value will take on, I look where the maximum value is. Like this is the maximum value. And so this rectangle kind of represents the biggest area that our so this rectangle is like our upper bound on the area of the integral, right? And then similarly, our lower bound on the area of the rectangle, on the area of the on the area in the interval is simply taking that minimum value, which is at this like a, and then forming a rectangle. So our minimum value is like some negative number, this, right? And we know that the actual value of the integral is like this area plus like whatever this area is, right? But at least this max-min identity allows us to find an upper bound and a lower bound of it in a logical manner. And so that is max-min inequality. And then our final one is called domination. Alright, so what does domination state? So if we have a function f of x that is always greater than or equal to g of x on some interval a to b, that implies, so this is like an implication, that implies that our integral from a to b of f of x dx is always greater than or equal to our integral from g of x dx, a to b. And this kind of follows from the max-min inequality. If we know for sure that all our values of f of x are always greater than the corresponding value for like the same x value in g of x, then we know like the slice of area that we're taking from f of x will always be larger than g of x or equal to, right? So if this is the slice that we're adding to form the total area from f, our g will always look something like this. It will always be less than, right? So that means our overall area that our integral evaluates to will always be greater than or equal to compared to the value for g. And an implication of this is that like this is any arbitrary function, right? So a function that g of x could be is just simply equal to 0. So then if f of x is greater than or equal to 0 on some interval a to b, that tells us that the integral from a to b of f of x dx is greater than or equal to 0. And we saw that, right? If a function is always above the x-axis, right, it's always positive on some interval, then the area that we calculate under the curve will always be greater than 0 or equal to it if it's always flat. So that was the domination rule. And so let's actually use some of these rules and let's put them into practice, right? So this is like example 1. Suppose we're given that some integrals and what they value to. So we're given from 1 to 4 f of x dx is equal to -2. And then we're given from -1 to 1 h of x dx is equal to 7, right? And so let us calculate some values. So what is the value from -1 to 4 of f of x dx? And so this is simply using the additivity rule, right? We know that this tells us the area from -1 to 1, and this tells us from 1 to 4. And if you want the union of those two intervals, we simply add this up, right? So this is simply equal to 5 plus -2. And so that is equal to 3, right? And let's do this one. So part B, this one is from -1 to 1 of 2 f of x plus 3 h of x dx. And so this requires a few rules. And so we know that we can split this up into two integrals. One of them is 2 times f of x dx plus the integral from -1 to 1 of, and then, okay, so this looks like a 4, but it's -1. Okay, -1 to 1 of 3 times h of x dx, right? We're given these values. So 2 times f of x dx on -1 to 1 is simply 5, and then plus 3 times 7. And so this is equal to 21 plus 10, which is equal to 31, right? And let's say we're asked to do something like -2 to 2 h of x dx, right? The only thing we know about h of x, like the function, is the area under the curve from -1 to 1, right? And we're told to find the integral from -2 to 2. But we have no information about h, and we have no information about like the rest of the interval. Like we don't know anything about the function from 1 to 2 or -1 to -2 to -1. And so if we're asked to do something like this, then we simply have not enough information. What if we're given that, but instead if we're given that h of x is odd? Notice that for odd functions, we have h of -x is simply equal to -h of x, right? And so the idea is, for an odd function, it's reflective across the origin, right? So if we were to split up the integral from -2 to 0 of h of x dx plus from 0 to 2 of h of x dx, right? On this interval from -2 to 0, like we're going to be putting negative x values, right? And because we know the function is odd and h of -x is equal to -h of x, right? We can simply rewrite this equation or this integral as negative from 0 to 2 of h of x dx plus 0 to 2 of h of x dx, right? And notice how, like, if we treat this as a variable that we don't know the value of, we have a negative of that variable plus the positive of that variable, and we simply get 0. So that's like one trick that I showed you. If you know the function is odd and we have like a symmetric bounds of integration, then we can claim, or I just proved how that makes the integral evaluate to 0. And that kind of makes sense, right? Like if we know like a common odd function is simply y equals x cubed, and that looks something like this, right? And so this area from like 0 to some x, and then this area of 0 to some negative x, right? Whatever this area is just the same as this area, like the magnitude, but it's just negative. So when you sum those up, you will always evaluate to 0. And that's what we showed there algebraically. All right, so those were some examples. Let's do one final example. Show that 0 to 1 of square root of 1 plus cosine x dx is less than 3 over 2. So this clearly shows that we're going to probably using the min-max identity. And so how can we use the min-max identity, right? We need to show that 3 over 2 is an upper bound, or like a strict upper bound at least. Let's look at the function cosine x, right? On the interval from 0 to 1, and we know that like cosine x starts at 1 and then hits 0 at pi, right? Pi is 3.14. So 0.0, like 1 is somewhere here, right? So on that interval, like we know the maximum value cosine takes on is 1, right? So we know that from 0 to 1, the square root of 1 plus cosine x dx has to be less than or equal to 0 to 1 of square root of 1 plus 1 dx, right? Because the maximum value cosine takes on in general is 1, right? So I'm upper bounding cosine x with 1, and then that is simply equal to the square root of 2 dx from 0 to 1, and then from before this just becomes a constant, and we know how to find the integral of a constant, right? So this is just root 2 times 1 minus 0, which is equal to root 2. And root 2 is about 1.414, and we know that is less than 3 over 2. And so we have shown this bound. All right. Now, the second part, I'll get to it later. I was going to talk about antiderivatives, but it seems like I've already spent a lot of time talking about these properties, and next time we'll talk about antiderivatives.